All right, welcome everybody to today's accelerated webinar. It's the Accendo Reliability webinar series, and today I'm going to round up a whole slew of questions and it's become more noticeable over the last month or so. We've been receiving questions about accelerated life testing. Is this a good approach? Is this a good option? What if happens if I do this? Here's an idea I have, or what's the downfall of this? You'll see I cut and pasted a good number of questions in here. And I did receive a few questions from people when we advertised this event. So the hard part is I'm realizing that there's a lot of content here, or a lot of questions to discuss and go back and forth. So I'm not sure I'm going to get through it all. So we may end up with a part 2 to this. And also, welcome Long Chun, is if you've got questions, please do at any point, throw them into the chat or the Q&A window. And if we don't get them to today, that's fine. Most likely we'll get back to you one way or the other, or another event. So with that, I'm going to dive into it. Let's see, there was, one thought is, by far, I don't have all the answers to all of these questions and all of the nuances of it and stuff. And sometimes it's how you interpret the question. So feel free to, jump into the chat window with how you would respond. What would be the issues you would bring up, and how would you approach, responding to these particular questions that we've received over the last couple of months. So let me see if I can get my slide to go forward now. All right. Now, accelerated testing in its absolute simplest frame of reference for me to understand it is that we're cheating time. We're doing something artificial to age something, material, a hinge, a door, electronics, or whatever it is. We're doing something so that it behaves like it's older than it really is. Now, after spending the weekend splitting firewood and gathering firewood and using my chainsaw, I think that was an accelerated test on me. So it's Tuesday now, and I'm just slightly recovered. Although some systems recover, many don't. And a lot of things that we work with are, corroding or diffusion or all these different mechanisms. Yet those mechanisms take time in the natural world to occur, in some amount of time. And we're often trying to do is say, will it last this long? Will it survive 5 years or 10 years or 20 years in some environment, some use case? And so we use a wide range of tools and techniques to basically cheat time, not have to wait until the normal time expires, and then we learn our answers. Now anybody that's talked to me about accelerated testing is usually the very first or very early question from me is, well, what's the mechanism? What's the physics or chemistry or fundamental process that's leading to the failure that you're interested in? And sometimes I'm more interested in what's the failure you're interested in, which may lead to the question about mechanisms. Yet I'm a firm believer that if you're involved with accelerated testing, you really need to understand what is the process, is in a generic term of the chemistry or physics or whatever, that actually responds to the stresses leading to the failure that you're interested in. So if it's solder joint fatigue, for example, and it's cracking, there's a solder joint fatigue mechanism that is at the materials level, is a process you can get into great detail about. And we know that thermal cycling is a method. It's not the only method, but it's a method to approach exciting that particular mechanism, make it go faster or slower. And we all did this as kids. Well, I think most people did, is you take an aluminum can and you first enjoy the contents, and then you bend it in half across its equator and bend it back and forth. And eventually that aluminum will rip open, or it'll crack all the way across, and you have two halves of an aluminum can. That's one way to destroy an aluminum can or make it smaller. There's lots of other mechanisms, but if you're interested in crack propagation, that might be an approach. If you're interested in its compressive strength, then standing on it to make it smaller might be easier. And you might have noticed early on that larger people with bigger shoes can crush a can faster than others. The point is that the mechanism and the approach, the stresses and the technique we're using are intermingled. You got to know the mechanism in order to apply the appropriate approach. And it's, while this isn't a webinar on accelerated testing, I'll leave it as that. It's kind of some of my, I don't know, thoughts about the topic before we get into the questions. And then the final note to consider here is that when we're going about doing accelerated testing and setting it up, it almost always is a set of trade-offs. You know, we may use one approach or technique that we hope will shorten the time, but not cause too many false failures or failures we're not interested in, or it'll give us a reasonable answer, and so on. But there's always trade-offs, and it might be budget, it might be time, might be number of samples you have. It's very, very rare, and I probably could say safely never, I've run into an accelerated test that did not include trade-offs. So there might be a right answer or a great answer, yet the best answer is the one that fits within all the trade-offs and constraints. So this is a long way of saying that there's a lot to consider, and there's no one right answer oftentimes. So how many ways have you run ALT? You know, I'm suspecting that you've done some of this, that you're interested in it, or you're familiar with it. And looking at who's attending, I know some of you have got a lot of experience with this. So how many ways, different ways, approaches have you used just running it faster? Just using the, say, I think one of Carl Carlson's favorite stories is he started in reliability with a lab that was testing car doors, and they had basically a system set up, a mechanical system that would open and close car doors, and then they could test it after 1,000 door closings and check for wear and stuff like that. It's just use it more often. And there's other more sophisticated ways or different ways of doing it. How many ways have you done this? So it's not a rhetorical question. This is so you can find the chat window, and I can get a sip of coffee. High temperature using Arrhenius, okay. Multiple cycles over a shorter time. Yeah, increase the speed, like the door slam thing. Good, good. All right, couple of ways. I'm sure there's more. Okay, so I'm gonna dive into the questions here. Vibration levels, shock. I've always found vibration to be very difficult with acceleration. Debris load, well, that's an interesting one. I know about dust and stuff like that. Debris would be cool. I'd be curious what that's about. Multiple environment over stress tests. I think that's what MEOST stands for. Yeah, I've heard about that. I haven't actually run that myself. I've seen it run. Good, good. Couple different ways. So ORT, accelerated life test, was a question I got a couple of months ago, actually. And you can read the question here. And their intent here, time compression, that's a good term, Dan. Thermal cycling, our test, corner voltage temps. All right, Mahendra, good, good. So the gist of this one is they're planning to mimic some years of life through thermal acceleration. Now, the piece in the first sentence is it's on a new product line. So imagine this is a device. I have no idea what the device is. It wasn't in the question, but let's say it's a handheld GPS. I think they're still made, but years ago, I know that was a product. Let's say you're creating a new handheld GPS. It's got electronics, it's got buttons, a user interface, a display sometimes, most of the time, an antenna, kinds of cool stuff on it. And then they said, we're going to mimic years of life through thermal acceleration. So what's the problem with that? Why would I bring those 2 points up? That made me start asking more questions right away. And then they wanted to use the Arrhenius model. All right. I started, with just the first 2 paragraphs, I was like, well, wait a second here. If you've got a whole product, and let's say there's a simple product, 100 components on it, some ceramic, some plastic, a metal dome switch, for example, maybe a LED or LCD screen of some sort, or some other technology for a screen. There's a handful of silicon devices on it, and a circuit board, probably connectors. Just in that very, very short list, I think all of us could come up with a couple of 100 different failure mechanisms. Everything from fretting on a component where the metal to metal contact has slight motion and it creates corrosion, builds up and has it go open, to solder joint fatigue, to somebody drops it and maybe it's not watertight and you get some kind of corrosion. It wouldn't take long to come up with a lot of different mechanisms. And some, like shock, have some, but it's hard to argue that it's got a great correlation of acceleration when it's thermally accelerated, other than if you try to pick up a very, very hot handheld device, you probably drop it. And then you'll have this shock related damage. And the idea here is that if we're going to use the Arrhenius model, or any model that's related to acceleration factors, that we're trying to understand the relationship between a higher stress level to what it would occur in normal stress levels, is there a mechanism that is actually accelerated by temperature that we're interested in? And if it's a whole product, there's more than likely a whole slew of different mechanisms at play, some of which are accelerated by temperature. Some are, related, have some relationship, maybe very weak relationship to temperature, and others have no relationship to temperature whatsoever as an accelerant or as a stress that applies on that mechanism. And if the dominant mechanism is nothing to do with temperature, then it's hard to understand how you would create a model that relates it. The other part of it is that just within temperature, silicon has a diffusion related mechanism that has a activation energy, which is what you need for Arrhenius equation, acceleration models. But the polymers have a different activation energy. The handful of other materials, capacitors and so on, they have different acceleration factors based on different rate of chemical reactions occurring. And so I'm very, very cautious about doing any kind of acceleration on an entire product unless you're particularly concerned about a specific mechanism. Now, let's say it's some diffusion problem that's occurring that would, your antenna has to have this certain mixture in it, and diffusion would destroy that. So we can accelerate that with temperature. It has its own activation energy, and then it might make sense. Where we're also ignoring all the other mechanisms and hoping that the temperature increase doesn't accelerate them so fast that it messes up the experiment we're most interested in. All too often, I've seen people say, well, I'm going to put it in a high temperature chamber. We'll assume an activation energy of 0.7 electron volts and pretend that that's telling us something about how long our product will last. And that's frustrating, because you get a number, it just won't be all that terribly useful unless you're incredibly lucky. Let's see, I'm looking at some of the codes. William's talking about the difference between, another quote coming in. qualitative ALTs like HALT that are used to discover failure modes, and quantitative ALTs designed to get an estimate life. Yeah, I'm only really focusing on the latter one, the quantitative ones. Is what's ideally at the end of the day, you say we have this probability it'll last for 10 years under these conditions, and we run accelerated conditions to create a probability density function of some sort to be able to answer those questions. It doesn't always work that way, but that's the general type of testing I'm talking about here. Let's see. Questions are coming in. So if you don't know the failure mechanism, do you have some pre-testing, maybe HALT, to determine what's going on? Yeah, you're exactly right, Robert, is don't go throw stuff in chambers and make a bunch of assumptions unless you have a pretty good idea of how those accelerated conditions, if they're even accelerating anything, apply. What's the model you're going to use? And that, in my experience, it really means you know what the mechanism is. What's the fundamental physics, chemistry type thing that's going on? HALT is a way to discover some of those. FMEA, engineering judgment, what's keeping the team up at night? What are the things you saw in the prototypes that have failed? What's in your past history? Use all the various means to figure out, well, what is it that you're most interested in? And it may or may not make sense to test it at the entire product side. Now, one of the best ongoing reliability tests, ORTs, I saw was mimicking different use conditions in ambient temperature. It wasn't at different temperature ranges people would use it or different altitudes or anything, but there were people that would use the product on occasion, maybe once a weekend as a hobby, or as a professional. They used it for 6 hours a day, every day during the work week. So think of it as that the amount of button pushings that occurred, the amount of transactions it would do, the number of door openings and closings. My car doesn't have near as much wear on the doors as a taxi would. So think through, what is it that you're interested in? And maybe it's related to the different use conditions of your customers. So sometimes not using something leads to interesting failures. And sometimes using it a whole lot of times leads to completely different types of failures. So ORT's got a whole discussion all by itself about how to go about doing that, make it work. Yet this question made me think that a whole product, thermal acceleration only, and we're going to use the Arrhenius model. Well, there's a raft of questions just in that one all by itself. And I haven't even gotten to the calculated MTTF. Those that have heard me talk before about MTBF and MTTF know where I stand on that. And that's a subject that was yet another question and pushback on this one. It's like, yeah, you need to know a little bit more information. There's a little too many assumptions here on the surface of this very short question for me anyway, to be comfortable with this approach. Yeah, Dan's talking about breaking it down into subsystems. Sometimes you got to go all the way down to component level or base materials. It's so dependent on what you're trying to examine or evaluate or measure. Well, that's just one question. I think I got 15 or 20 questions in here. Like I said, I may not get through all of them. So a couple of people, this is one of a couple of questions I gotten over the last couple of months. And it was, is there a table someplace that lists all of the parameters and all of the different failure mechanism? And they were interested in for humidity acceleration and then also for temperature acceleration. And a similar question was, is there someplace I can go to for a listing of, a listing of all of the failure mechanisms for each electronic component? And then they also added, well, also mechanical systems and motors and, gearboxes and all kinds of other stuff. That's going to be a long list. And then, how about different material types? What are the common failure mechanisms for, say, a Kevlar material, polymer of some sort versus a particular type of stainless steel? This is going to be a long list, a very long list. And is there a list of all activation energies for each mechanism? Well, one, not all failure mechanisms have an activation energy. Activation energy, to me, assumes that it's related to the Arrhenius equation. And I'm sure electron volts and activation energy may be used in other models also that are not, or might be similar or built off of the Arrhenius equation, or maybe completely different in the world of chemistry. But things like a corrosion, like rust, that's a chemical process that I'm very confident that a chemist could help you either find or look up, or could do an experiment for your particular material set for what, and stressor. Is it oxygen or is it some other type of chemical reaction that's going on? And they could probably figure out what your proper activation energy is. The hard part with a table in a book is that, is it your product with your materials, with your technology, with your assembly process, with your environment around it and stresses applied to it, or not? Yeah, I've seen tables where it says, for a bond joint, and Kenneth was listing 0.3 EV, but then I see another table that says, well, that depending on the type of bond and the type of metals involved in it and the process parameters being used, it could be from 1.5 to 6 or to 0.6. And at that point, it's not a terribly useful one, other than to say, hey, you need to go figure this out on your own. What I don't recommend is just assuming that it's 0.7. And I saw one person say, well, we're going to be more conservative than our assumed 0.7. We'll make it 0.9. I'm like, okay, well, what if it's 0.11 or 1.1 or some other value? Then you're not being conservative. You'll get a wrong answer. If you don't know the real answer, especially if you know it's a chemical process, well, go talk to a chemist. Go run the experiments of how to actually determine an activation energy for your particular chemical reaction. That can be done. We don't need to look it up somewhere. We don't need to go hallucinate what it is. Same with humidity. Humidity acceleration oftentimes is related to a chemical process. The moisture in the air is part of the reaction. It might be the water, it might be the oxygen, or the contaminants that moisture carries over for you. The part of setting up to me, a reliability test that's going to give you reasonable answers is that homework part. And it's not just go look it up in a table someplace. There might be a technical paper that's really close or right on target for what your particular situation is. And that might be a better place to start than some generic table someplace. The ones I see in textbooks are, for the student to run out some exercises or to give you a ballpark of what it could be in general, and some are better characterized than others. Yet, as all of you know, is the rate of change in materials and structures and processes for attachment and all of those elements continues to evolve so very fast that is very, very unlikely that what worked in the 70s as an activation energy for a particular process will work in your circumstances, because I bet you the materials and the processes used to create your product is probably quite different. I don't know what Kenneth, I've heard 0.5, I've heard 0.7, I've heard 0.9. They all give you dramatically different answers in your acceleration model. The hard part is, it's not hard. It's go talk to a chemist. Go talk to somebody that actually has the ability to, for your particular circumstance, to experimentally determine your activation energy. In my circumstance, we had a chemist working in the buildings. I went over and knocked on her door and asked, oh yeah, I can get you that. What's the circumstance here? What polymer are you using? It's the oxidation process, right? And yeah. And she said, all right, yeah, come back in about 3 days. I'll give you an answer. And they ran a quick experiment. They could measure the activation energy. And it's like, I don't know what she did or how she got to that number, but she ran an experiment to confirm what she thought it would be. And that's what I used. And then later, when we ran the experiment, one of the steps was to confirm the activation energy. So we used it as a fitting parameter, and it was within 1/100th of a point. So I thought, yeah, that chemist was right on. That was exactly what I was looking for. Yeah, yeah, different greases. It's not just different greases is different activation energy. It also could be that if you're in an engine, inside the engine compartment, you have petrochemicals floating around, that has a different interaction or solvents floating around versus water or salt water. Each of those different combinations of materials is likely to have a very different activation energy. So that's just Arrhenius. In humidity's got its own set of model parameters, on and on and on. Each of these different acceleration models that we use has parameters, and they're often in the technical papers related to a very specific set of conditions. And so if those match to what your circumstances, great, you got gold there. You can work with that model directly as is. Oftentimes, though, the grade of material they're using is slightly different than ours. Be very cautious, because it's very likely that those model parameters will be different. And so in setting up a test, especially if it's an important activity, it's going to be a critical decision somebody needs to make and worth a lot of money, spend the time to make sure you've got the right model parameters. And sometimes that means running the experiments to determine those model parameters, which has all of the attendant difficulties and experimental error and everything else that goes with it. Yet if it's important, don't assume them. It's kind of my basic message here. All right. Degradation. I'm stumbling over that word today. A lot of the images today are showing, basically wear degradation from all kinds of different sources of stresses, from wind and air and all the other stuff, of how it shaped our landscapes. Just think of this as like the surface of a solder joint or something like that for these images and how they change over time. So here's a question that was, they wanted to do something better than assuming an exponential degradation, which well, that's cool, because I don't think exponential distribution will necessarily describe a degradation mode by default. There's lots of different patterns and paths. Can we use a life data approach? And they were talking about, what kind of data do we need to collect? It's done in Minitab or Excel. Summarize, I got all blah, 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 help or advice. And so the upper part of this question I didn't reveal because it had a little bit of identifying of what the topic was, but it was clearly they were measuring degradation. It was a degradation failure mode. So something was wearing or eroding, but causing a decline or a change in performance, and they can measure that performance over time. Think of like a LED light is an example I use, is that the amount of light that comes out of it, the power of that light, or I'm trying to think if it's lumens is the right metric or not, but anyway, it will slowly degrade over time into where that LED is not as bright as it was before. And so it was a performance measure that we do. How bright is it? Right. And it changes over time. My very first ALT was on the resistivity of the system. And as it oxidized, the resistivity went up. And so it changed the performance parameters of this particular system. And so it was a degrading of the performance. And the failure mode is probably the right one. It's a symptom of it. At some point, it becomes not bright enough, say for an LED, and then we say it's failed. It's still emitting light, but it's not like it used to be, or it's not the right color or something like that. Now, the issue I have here is that life data analysis where I have time to failure data. I take, say, a whole bunch of LEDs and fire them up at say, different voltages or different powers feeding into each one of them, 3 different sets of stresses, and I run them all until I get a bunch of failures. I think you can do that. I think that would be an approach. And I know there's and there may or may not be issues with that approach, depending on the path of the degradation. Is it linear? Is it not linear? Things like that. But it is a approach. I agree. Although I argue that if you can measure the decline of, say, how bright these LEDs are over time, well, let's use that. And I don't have to wait until I get all the way out to failures. I can run some of them out to, say, 80% of their initial brightness and call that a failure. But I have the path that the others are following. So I can probably project when those others are going to cross that line that we define as a failure. And so instead of running out until we get indications of failures, assuming that we can catch it when they cross that threshold, when they go from being bright enough to not bright enough by our criteria, let's measure them periodically and measure their rate of decline, and so that we can project when they go to failure. It's a slightly different way of looking at it than measuring just time to failures. Here we're measuring the data to project when it goes to failure. Now, can you do this in Excel or Minitab? I don't know Minitab well enough. I know Excel can do anything if you're patient enough and hard and use or a wizard with it to some extent or another. There are other packages out there you may want to explore. But it's a good question, is what data do I need to collect? And that's, I think, the key from this one is, if I'm measuring degradation, what parameter is important? How do we define failure? If I'm measuring time to failure, ideally we do a continuous measurement of it, so we know to the minute or second how long it took before we started the test until it failed. But sometimes that's not possible. The stress conditions would destroy our measurement system. So we have to take them out of the high stress. And in worst cases, then your product is temperature sensitive to what kind of readings you get. You got to bring it back to use conditions or cool it off or heat it up, whatever the stress was applied. And then make those measurements. Now you might only make the measurements once a day or once a week, if you're lucky. And now you have interval data. And it has its own nuances to how that's analyzed. It's ideally, you let it run in normal conditions, you measure it until it's defined as failure, and it's continuous monitoring, all these other great things. Yet if we want to cheat time, we may increase the temperature, we may increase one or more of the other stresses that are involved with this mechanism that's causing this degradation, for this example. But that often then takes us further away from the use conditions. And so this gets at what I see it as a number of questions. How much stress can I apply that's still relevant? And how do I analyze the data? And what data do I need to collect? It's not as simple as throwing it into a chamber, assume an activation energy, and call it a day. Trying to illustrate with some of these questions is that, yeah, you need to step back and think this through a little bit of what you're trying to do. At least in this question, it was like, well, what kind of data do I need to collect? I think that's an excellent question as you start designing an accelerated test. What exactly can I collect? What's relevant to what I need to know? And that couples with, then, well, how do I analyze it? Do I have the tools and technology and wherewithal to do this? So there's plenty of back and forth in this early stage, just around what am I going to go measure? And I think that's a very, very good question. So I reinforce that one a whole lot. Yet there's also, as soon as you start seeing a degradation, there's a whole type or methodology around dealing with degradation type data, which is different than time to failure data in a couple of slight different ways. Let's see. Yeah, David's saying degradation testing provides more information. It has its own what I like about it is that you tend to get an idea whether the path to failure is linear or not linear. Maybe there's some other phenomena going on that's accelerating the rate of degradation or decelerating it, actually helping your product last longer before it hits the threshold of what we call failure. Whereas a time to failure one may or may not reveal that kind of information. Depends on how you're measuring and how you're looking at those measurements over time. Let's see, Dan, I'm not sure I understand the comment. Is you also need to understand the behavior well enough to know if the suddenly starts behaving exponentially. I imagine if the pattern starts behaving or the data starts behaving that way. Still not really sure. Yeah, I have a UV lamp that behaves like a hockey stick. Yeah, I'm thinking of the hockey stick reference there, Dan, is the Weibull plot where all of a sudden it just goes straight up, basically, as the end of the stick. And it's usually a signal, not always, but usually a signal that a failure mechanisms is taking over. There's a degradation for a while, or there's a pattern, a time to failure for a while. And then I had one of these with an optocoupler at 8,000 hours. I never did learn what the underlying mechanism was, but there were some assembly problems and there was a handful of infant life mortality and a couple other issues with it, but very rarely would it fail for the first 7,000 hours. And then all of a sudden they'd all fail at between 8,000 and 850 hours, 8,050 hours. It was amazingly fast how quick whatever it was decided to wear out or fail happen. But a lot of times we've got some information or data, or we've got some stuff to give us clues as to how to go about doing these accelerated tests. So use all of that info as you go into these things. Okay, a couple more questions. This is one I ran into early in my career and I run into over and over and over again. One of my favorite applications of this PEX equation, which deals with the accelerants of temperature and humidity. And it was a model that was empirically derived. Originally, PEC gathered, I don't know, 100 or so different experiments and had time to failure data basically on each of those. And then pretty much just aggregated all those different experiments and created a model that described them. And it wasn't like it was from first principles or anything. It was just, we know that temperature and humidity are accelerants on, and this is the part that gets me all the time, it was early on in electronics, we were moving from putting component active elements like silicon in metal cans that we would seal, and we were putting them on just a little platform of the traces that were connecting to the active elements, and then using epoxy to seal it instead of a metal can. It was faster, it was smaller in size, it had thermal properties that were nice, it had a bunch of other benefits for it, but it was new. And a whole bunch of different experimenters went off and were looking at the phenomena that if that epoxy was not bonded properly to those little copper oftentimes or metal leads that were coming out of the component that you could then attach to the circuit board, if that wasn't sealed properly, moisture and other contaminants would work their way in and cause the silicon devices to fail, usually due to some kind of corrosion. So accelerating using temperature and humidity was found to be a pretty good predictor of if this was well bonded or not. And so a bunch of people were trying to figure out ways to accelerate that test using different temperature and humidity stressors. And it was run at all kinds of different combinations, and it's a complex problem with just two accelerants. And so they had all these experiments and they pretty much put them all on a big old plot. I'm oversimplifying Peck's work, but he put him on a big plot and then drew kind of the average line through it and then said, well, that's described by this model. And that became Peck's equation. What's really frustrating is I saw it being used on entire solar panels. People were putting solar panels in these great big temperature humidity chambers things. And it's similar, I grant it, they're sealing the active components of these solar power conversion, the active elements of it were being sealed inside under glass or plastic with edge sealants and everything else. But they were using the exact same parameters that Peck used on epoxy on a lead frame. And I was like, the probability of that actually being the same is low. And do you have any substantive evidence that that's the case, that you should use 2.66 or 2.7? And he said, no, it's a temperature humidity model, so we're going to use it as is. And that was just one of many, many different types of products that I've seen, some unrelated to how well two components materials seal, that use temperature and humidity as an accelerant using this equation based on epoxy sealing on a lead frame. And they'll get an answer and then be frustrated that it doesn't relate to what they're seeing in the actual use. I was like, well, there's, go read the original paper or think through what we're trying to actually do. And does this really apply? It's one of my pet peeves with industry standards. They say, here's a model for you, but they don't tell you what it's used for, where it applies and where it doesn't apply. Now, in this question, it was, well, what if I just change those parameters so I'm a little bit more conservative? Does that work? And it says, well, there's lots of ways to account for experimental error or to deal with some of the uncertainties with doing an experiment. Changing the parameters is one. I think it's way more important to make sure you've got the right parameter to start with based on the particular mechanism and structure you're dealing with. But the backing up from that is one of the techniques I saw used pretty commonly for solder joint fatigue is we were calculating basically how many thermal cycles before failure, and then we would double it or cut it in half. We would divide it by 2. So if our experimentation said it would be 10,000 cycles before we saw some percentage of failures, we would cut that number of cycles in half as a conservative estimate to account for experimental error and uncertainties. I don't know why they picked 2. They could have picked 3. They could have picked 1.5. I don't know why it was cut it in half, but that was the standard practice in this one team I was with. It always came to be a push, though, as to if we use the straight data and it was good and we went conservative and it was bad, then there'd be an argument about, well, how conservative do we need to be? Now that's outside of just running the test, but it's important in communicating the results and making these assumptions about trying to be more conservative. Let's see. Jason's asking, do you agree that the acceleration factor for temperature humidity shall not be more than 30 to 50, which need be concerned? That brings up a whole question about your acceleration factor. Yeah, sometimes you get incredible acceleration factors, and 30 to 50 is not unreasonable in some circumstances. And you're exactly right. Is it linear? Is it still apply out there? Does it make sense? And I think there's another question coming up, which I may get to, that talks about it. But the idea is that, yeah, if you get an acceleration factor that's 10,000, or I'd say even 20, start asking, is that real or not? Realistic, I ask that question even if the acceleration factor is only 2. Every cycle in the lab counts for 2 cycles in use. Well, is that giving us the exact same or very, very similar failure mechanism? Does it fail in the same way? Is it the crack propagate in the same kind of structure? Is it shearing, or is it ductile failure, or is it some other metal phenomena that's causing this to occur. Part of it is, in any of these experiments, is the failure analysis and understanding the details of what types of failure, nature of that failure, behavior of that failure that you're interested in. Is that actually happening? If you throw a complex system into a chamber and just measure time to failure, so the little green light goes off, well, as you know, and I mentioned earlier, is that there might be a lot of different ways that little green light goes out. And it may or may not be of any interest to you, because the acceleration of everything in that system that can be accelerated by, say, temperature, is going to do it at its own rate. And some failures will be accelerated very, very rapidly when it gets too far outside of use conditions. But we know from the science of it that we don't worry about that. That's a failure that's just irrelevant and very, very low probability in normal conditions. Yet in testing, it gets accelerated artificially very fast, or not artificially, it gets accelerated very fast with that stress that's being applied, and then masks or hides or fails before the ones that we're interested, that we are not certain it will fail, at what rate it fails in use conditions, because it has a different reaction, to the reaction being a chemical or a response to the stresses that are being applied. They're all not the same. And so first, if you're using a model, does it apply to the parameters? Are they sufficient to describe your particular circumstance? And then if you want to be conservative, there's a number of approaches for that. But I think that's lower on the case of running a solid experiment, having plenty of samples. If you still want to be conscious, it's up to local policy, is how cautious you want to be. Is it rounding down, or is it cutting in half, or whatever your local risk tolerance is? All right. I just saw a warning come up on my Zoom thing, and I was like, well, I hope I'm still working here. Let's see. Got another question here from Derek. Since ALT should target a specific failure mechanism, oftentimes that means testing at lower system levels or even component level. I agree with that. And sometimes that's for how do we apply the stress? How do we save money? How do we get enough samples? Some of those problems are improved by going to subsystem or component levels, or even material level. Think of accelerating a coating on a surface. You don't need all the other wizardry that's inside that box. You just need some coupons with that coating in a similar process, or same process of application. So then he goes on. Reliability requirement at lower level is usually quite high compared to parent system. That's true. So it becomes prohibitive to test long enough or with enough samples. Again, true. Especially if you need to determine your own acceleration parameters in, like activation energy, for example. There are other approaches. Are there other approaches worth considering? I ran into, I was working with a client, and I was on one part of the system. I was working on the game controller, related to game controllers, and the game console, which is a much more complicated and much higher powered thing than a handheld game controller. Their lead reliability engineer came in and said, well, one of the products your team works on is, and I didn't even know it existed, but I suspected it was someplace, was this little circuit board that creates it wasn't Wi-Fi, it was some other technology that sends and receives messages to the game controller. Since you guys have been making these things, we require you to prove that it meets its reliability requirement. And so they had done the apportionment from the whole system. And I think the reliability requirement for this very, very small circuit board with maybe, I think, 10 or 15 components on it, and one connector for power. And it also had the digital signal coming off of it and to it, so on. So it had maybe a 6-pin connector and say a dozen or so components. And the reliability requirement was something like, I want to say part per million. It was in astronomical things. So, and I said, have you attributed any failures in the field to that component or to that subsystem? And they've been making it for a decade. No, right? If it fails, can the consumer just plug in and keep going, or is it easy to repair, or is it, what's the consequence it goes? Well, it's inconvenient, right? And I knew they were struggling with their CPU and memory and a bunch of other stuff with very, very high failure rates. And they were trying to sort all those things out. And he says, you're telling me you want us to spend all this money, which comes out of our combined bucket for doing all this stuff, to go prove something that you really have no indication whatsoever that it's an issue or will ever become an issue? And he said, yes, we're asking every single component supplier. He said, you're going to a capacitor vendor and asking them to prove exhaustively that they are at two failures in time, part per billion type failures. Yes. So what kind of evidence do you require? And he just started going off and full on testing and demonstration testing and all this other happy stuff that would require thousands and thousands of samples and chambers after chamber after chamber. And I says, do you want me to tell your boss how much money you're wasting or do you want to? And he left the room and didn't talk to me again. There's some things that we need to experimentally solve, and it's important. It makes a difference whether we use this vendor or not, or this approach or not, or this solution or not. And there's others that really don't. And just because we can estimate through testing that failure mechanism or that time to failure or that model doesn't mean we need to. I mean, oversimplifying it, we go to the 80-20 rule. 20% of our components are causing 80% of our failures. And it probably is smaller than that in most electronics, most systems I'm aware of. But the idea is that let's focus on the vital few and put our resources and energy into those and knock those down, because the chance of this little communication board failing and causing this console to fail is minuscule compared to the problems they already were working on, but were strapped for resources on. And here's this guy going to go spend millions of dollars to chase these phantoms that are out there. Now, yeah, there is a finite probability this board would fail. Yet they had no recorded case of it ever occurring. And yeah, it's a new console, it's a new box, it's going to be a little bit higher temperature because of the power it's consuming. But do you really need to solve this problem today? It was kind of the argument back. That has a utility, yet you need to do your homework to know what the risks are. What's the chance of this failing and what's the evidence you have for it? Then if it is critical, you need to do it, then let's go do the homework and get it right. But the basic notion that you need to go test everything, I think, is folly. Testing's expensive. Let's use those resources to get really good answers on the critical few that we do and not on everything. Yeah, Dan, somebody go test Teflon to see if it oxidizes. I don't know, does it? I had no idea that it would. It probably does. It's a polymer. But yeah. I've also had people say, well, just throw it in the chamber and see if it works. All right. So I threw it in the chamber and it shattered. He says, well, you didn't tell me it wasn't a drop test kind of thing. He didn't ask me to run any more of their tests for them. That was a short-lived client. Anyway, PEC's equation and a lot of the well-documented equations that we see out there, they typically have a very specific application. And when you deviate from that particular application, all bets are off. It may or may not be right on for what you need, but do the diligence to figure out if those parameters are the ones that you need for your circumstance. And then once you prove that to yourself and you're still using that technology that you've created your own parameters for, well, then you're good. You got a model that applies for your circumstance. Be cautious, though, as your design team changes materials or changes processes, that those parameters may change, and be aware of that. But yeah, there's a lot of great references out there and a lot of good technical papers that provide models and fitting parameters and so on. The caveat is your mileage may vary. And depending on the magnitude of the importance of what you're working on, you may get in big trouble just by assuming that you got a right answer and you really don't. And that can be, that just be careful using out of the book type stuff for your particular circumstance. I think a handful of questions have come across in that regard. I think I got time for one more, and then we'll see what other comments and questions you have. So a more recent question came up as, well, how do you compare two accelerated tests? And say, let's say the question is the difference between two populations. So I'm thinking right off the bat, it's a hypothesis test, but that's just me. And that may be oversimplifying it or making it weird, but you got two populations. And so population A, population B, we're doing a set of tests and we get two different results in our acceleration. The time to failure at some key point we're looking for, or the overall, how many warranty claims we're expected to have. So the basic answer to this, the start of this one is, well, what is it you're trying to learn from the comparison? Is it the expected number of failures you would have, say, over a warranty period? Well, then estimate that the early tail of your the probability density function, and how many samples or how many units are you expected to ship, and how many failures you're going to get, and then compare those two numbers. If you're really fancy, you could probably use a couple of fancier techniques to figure out what's the variance of those answers and actually use hypothesis tests. But it's one way to go at it. I've seen another one where they say where you just plot the two on, say, put them on a Weibull plot. And the caveat there is that is the Weibull distribution really adequate to describe your time to failure distribution? The difference between Weibull and log normal matters sometimes, but not all the time. So be careful if one's well explained, described by one distribution and others by another distribution. If you put them force them to be both Weibull plots, you may be masking or altering how it fits that data to mess up your comparison. But let's say they're both Weibull, they both have characteristic lives, and they both have slopes or beta values, and plot them. And then you can interpret, from year 5 to year 10, vendor, solution A is better, and then at this time solution B is better. Which one's more important to us? You can make a decision. So plotting can work. To histograms of those, basically to plot the two probability density functions. And so another technique, but I like the cumulative distribution function for that. One that I found very difficult to do is to compare the parameters. What I've learned, and I know there's a handful of folks here that have more experience with it, but in order to get a really good estimate of a parameter, say the beta parameter on a Weibull distribution, takes a lot of samples before that confidence starts to come down to be something worth making comparisons. So some of my early experiments, we had a couple hundred samples at 3 different levels, and we used those to estimate these parameters. And the confidence bounds on the parameters themselves were huge. So I don't remember those particular numbers, but let's say it was a beta of 2. It went from a low of 0.8 to a high of 3.4. And I had, hundreds of samples. So I did some calculations saying, well, if I really want to understand this beta, that it's above 1. So if I get an answer of 2, how many more samples, how much more detail do I need, basically, so that I can convince myself that it really is a wear out mechanism, or it's a beta that's greater than 1. And I was at 0.8. Says, well, that's not that far away. And it was like 800 or 900 samples, 3 times what I used in order to to have a better estimate of that variability of that fitted parameter. And I thought, wow, that's expensive. So, and since then, I found that the parameters, yeah, you can get confidence on those, and you can compare parameters like the characteristic life or the beta parameter. Yet you need a lot of data before those things will give you a conclusive answer that this is better than the other, or they have to be amazingly different from each other. So that's a hurdle I ran into is if you're looking at comparing two populations, the first question is what's important to you? If it's the number of failures, well, then compare how many failures each of these populations will create or likely to create in the period of interest. But start with what do you need to know? What are you making the comparison based on? And then proceed from that. And so having two populations and it fitted curves to it, or even just the two populations or an estimates of those populations is a great place to start. It can answer many different types of questions, which then leads to different ways to make the comparisons. And the hypothesis test is just one of many ways. So with that, I think, I didn't get into this one, multiple stresses. Just be aware, this gets complicated real quick, but let me pause here. I think there's like one or two more screens with questions on it. And I'll come back probably another time to fill in some more and address some of the questions that came up and the stories that came up in the chat. That's great. But let me wrap it up here and say thanks for attending, and thanks for chiming in on the chat and a couple of the ideas and comments and experiences. It's all great. I'll stay on the line. I'll keep this open. If you've got some specific questions, or if you want to ask some more questions, you can send it in the chat. I'll keep track of that, or you can send me an email or get a hold of me with your questions. I'll try to answer sooner than later to you, but then it might make good fodder for another Q&A session on this. So let me know what you think of the style of webinar, or if you'd like to see some changes to the format, or other topics. What other things are as question generating, like accelerated testing? I'd be very curious of that, and see if that sparks another similar type approach. So let me stop the recording. Once again, thanks for attending.